Hello, everyone. Thanks for coming. My name is Mikko Mononen. I'm principal AI engineer at Epic Games. AI in the sense, not the machine learning stuff, but the old school smoke and mirrors. So today we're going to talk about state trees. State trees are general purpose hierarchical state machines. General purpose in the sense that it's just not for the AI, not just for pawns or actors or anything. It can be used just about anything in the engine. They're flexible. The hierarchy lets you efficiently reuse and build the trees, the behaviors, and users can get their own building blocks to use in the state tree. So they're extendable, and they're fairly easy to embed. So if you have some special use case that isn't covered by us, you can easily use state trees in different use cases. They're lean in the sense that we try to take a lot of care, making them efficient to run and memory efficient as well. At Epic, we've been using state trees. The first case was the city sample. We used state trees to basically describe and build the pedestrian behaviors for the 30,000 NPCs in the city. And in the Fortnite experience, we're using state trees for smart object behaviors, like when you're sitting in a chair, there's a little state tree there doing the sequencing, how to get out of the chair, and so forth, as well as doing encounter progressing. So, for example, that you have certain steps in your encounter, and we're using state trees to describe what happens when things should happen and what happens when stuff changes. And from our licenses, we're hearing that they're using state trees for example, combat action selections or animation selection or object states, just like us, or quest logic. Of course, like AI behavior is a thing that they started from, and that's what other people are using it as well. So today, I'm going to go through how state trees works and try to go to quite pretty neat detail. So it's going to be quite theoretical. And I try to kind of call out things that where I've seen that people have struggled either understanding things or they might be surprising for people using state trees. To get started, this is more or less how the state tree look like in the editor. If you're using state trees before, it might look a little different. We're working on a UI update for 5.5. And they're probably going to be even more different when it comes out. And just looking at the picture, we can see that, okay, on the left we have some global data stuff, and in the middle we have the state trees, states and the whole tree of them. On the right we have some details about the individual states. I'm showing this I'm showing like a more narrow screenshot later, so you have some kind of way for organizing them, how they might work in the big picture. And the bread and butter for state trees are states and tasks. And the state tree is basically hierarchy of states. They are organized in a tree. And looking at the picture, we can see that there are kind of roughly two different kinds of states. There are one which have child states. We call them intermediate states or selector states. And then there are leaf states, which are used usually for like the final activities, like playing animations or moving. And the intermediate states are usually used for state selection and organizing abstraction in your trees. There's one concept called active states. I'm going to use this throughout the presentation, coming back to it. And it basically means that if you selected the given child state, the stuff on the parent states are also going to be available. And this is a way to kind of reuse and organize the tree. Every state can have tasks, and these tasks are basically the things that will do the effects or actions or whatever that your state tree is doing. They're basically a piece of logic that has predefined beginning and end, and this corresponds to the state selection beginning and end. An example of task could be, for example, you're setting gameplay tags on your actor, or you could be claiming a resource, or you're playing animation or moving to a point. Just like we have the active states, the active states all can have active tasks. And each task further can have multiple tasks in them, and this allows basically you to create more fine-grained, reusable little tasks that can be used in multiple different places. And as hinted earlier, like the leaf states tend to have the real action happening, and the intermediate states usually are something where you configure things. Like in this case, we are setting the tags that now on all the child states, we basically have a certain tag being applied to the character or actor. And the task completion will drive the state completion, and we will come back to this later. Finally, we have global tasks. They are basically run for the whole duration of the tree. And these are usually used for things like if you need to do expose some data that is always available for the whole tree. Or like in this case, I have event listener tasks. That could be one use case. Or you might have something that you want to always do some cleanup on the exit of the whole tree, and that could be also a global task. It's guaranteed to run when we stop the state tree. So state selection, there's 3 parts to it. We have transitions, we have conditions, and then the selector states I hinted earlier. And first, the transitions. If you're familiar with state machines, nothing new. Basically, they define how to go from one state to another. There's 2 kinds of them. One is which are triggered on state completion, meaning that your animation has played, what to do next. And the other ones are basically based on events, and this could be that when the character gets hit, what to do in that kind of case. And the transition can be refined with conditions, and I'm going to talk more about that in a bit. And the one part of this completion transition is failure handling. That can be especially for AI. That's like a big part of the whole behavior. Like what happens if your pathfinding fails or so forth. So you can have transitions either that are run always, whether you succeed or fail a state, or when something only fails or so forth. Yes. And just like the tasks, the transitions also form a hierarchy. And that lets you build abstractions. Like if you always want to do, like on any of the open states here, if you want to always, on each of those child states, we want to have a certain transition, we can pop them to the state that is one higher. And the transitions are triggered from the leafmost state all the way to the root. And the idea there is that the leafmost state usually is the most refined. So if you need to override some common transition, you can do that on the leaf. And there's one thing I want to call out here, which happens when you have more complicated trees. And you might have tasks that kind of can fail in the middle on the intermediate stage. Like here, if the set tags could fail, we would start the completion transition handling from the middle of the tree going up. And the idea is that this is useful for the cases where you might not have initialized everything on the leaf states yet. So we start from the middle. It might not make sense now, but it will make sense when you hit that issue later. And transitions also have priorities, and these can basically use to break the rule that we start from the leaf and go to towards the root state. And conditions can be used to either as an enter condition for a given state. I'm going to talk about next about the state selection. We will see an example there. Or they can be used to refine the transition conditions. For example, you might have a damage event coming in, and you could have different transitions based on the damage value or some other value in the that you have exposed in the state tree. And conditions are fairly generic in state trees. They're usually dealing with floats or bools, and that's due to the data binding. That's how the data flow works. We're going to go into that detail later. And the condition can be organized in expressions. We have this quirky little thing where you have organized them in an array, and based on the indentation, they get grouped together. If someone is familiar with one of the Python ways to organize your conditions, you're at home, other people need to do a little learning. There might be a little gag reaction initially, but once you get past that, all kind of awesome expressions come out of it. So state selection, there's kind of like 3 parts to it. When we get an event, in this case, we get the player interacted with our little loot chest. We have open and closed states, and the open state has substate based on whether the chest has been already looted or not. So what we want to do there is that on interaction, we want to try to transition to the open state. Since the open state is one of these intermediate states, it can't be selected directly, but it actually will pass the selection to all the child states. And here we go first. As the looted state, can you be selected? It says no, because that's the state of the chest currently. So this is where the enter conditions play the role. And then what we're going to do next is we're going to go to the next state, and next that, can you be selected? In this case, idle says, yes, I can be, because there's no enter conditions. And if there was like a further substate, that process would go through all the way to the final leave state that has to be selected. And based on the leave state, we can figure out what is going to be the new active states. In this example, the new active state will be idle, open, root. Before it was root and closed. And one thing to note about here, that we haven't done any state changes yet. Currently, we're just looking what are the possibilities to do next. And finally, when we found the leave state we want to go to, we will call exit state on the states that are being left behind, that are not anymore part of the active states. In this case, the closed state. The root is still active because it's part of the new active state as well. So we do nothing with that. And the open and idle are the new active state that we are getting into. They get the interstate called. And this lets us our logic to be basically start and stop at really well-defined places. And one thing to note about here is that people usually coming from state machines, they would expect that first transition to take place, and then after that, like we would transition from closed to opened, and then we would further refine the selection. But that's not the case for state trees. It's more like a behavior selection trees where we actually need to find the final state before we do the transition. And people coming from behavior trees have often the issue that they think about, well, what's going to re-evaluate my enter conditions? And the answer is that you need to do a transition. So for bored people, it usually takes a little learning to get used to it. But the hierarchical selector thing basically lets you have these cases where we don't care about if we're transitioning from closed to one specific state, but we can say that any open state, figure it out yourself. That's where the selectors are really powerful. And there are multiple different types of selectors. What I just explained is something called try select in order, where it basically goes individual every child state of one of these selector states and try to select them in order based on the enter conditions. There's also something called try follow transitions, where instead of going to the child states, we try to follow all the transitions of a given state. This can be useful for grouping transitions together to a bundle. A lot of AI stuff we haven't used for this, but for example, action games, they might have so many transitions that it makes sense to reuse the bundles. New thing coming in 5.5 is a random selector, very useful for building all kind of behaviors. It basically does, it's similar to the try select in order, but it shuffles the children first before doing the selection. And one thing to note here is that we have a specific transition which go to next state, and the randomness doesn't affect that order. It's still going to be the order you author the asset. And finally, in 5.5, 5.6 timeframe, we're working on utility selectors for the states, which lets basically every single state to calculate a score, and based on the scoring, we will either select the highest score state, or you can also use that for randomness. Basically, if a state scores really high, there's a really high probability for that state to be selected. So together with the randomness scoring, they can be really it can be really kind of powerful tool for creating more kind of natural or unpredictable behaviors, if that's your thing. There's also a bunch of implicit transitions. By implicit, I mean the things that happen even if you don't set them up. The first one is when we start the tree, we need to go somewhere, and we're going to go to the root state. And even if you call the root state is the very first top left, even if you rename that to be potato, it's still going to be the root state. And the second thing to note is that if there's no completion transitions provided for a given state, we will go and look for the parent states. And if we get all the way to the root, we're going to select the root state. And this can be something that you hit early on when you have half-baked state tree that, okay, why did it go to the root? And that's like a good, if you go to the root and you didn't mean it, chances are it's one of these implicit things. The same thing can happen if you have completion transitions where they're guarded by conditions. It could be that you have, let's say, two completion transitions, both with some certain condition, or you have enter conditions on the target states. In both cases, if nothing can be selected, we will go to root. And the idea is that if your state is completed, we expect the state tree be in a state that it can't continue executing, but it needs to refresh the planning, basically. Finally, events. Events are basically something that we can send to the state tree. They are the most efficient way for doing transitions. Event can be a gameplay tag, or it could be a struct, or combination of both. They can be used to trigger transitions, or they can be also captured by used as an enter condition for a given state. So if you have a selector state and all the different states in there might want different events, you can use that as a filtering there as well. And when it's used as a enter condition for a state, it is also captured. So that's sometimes useful if you have, for example, do directional reactions or whatnot, you have the event data there available. As well, like when we do the transition, if the payload is also available for further kind of conditions on the transitions as well. We have events for a while, but there was a big improvement how they get handled in 5.4. So now we go to the data flow. So state trees don't use blackboards like BTs, but instead we allow properties of the conditions or tasks or basically to be bound to some other data in the tree. In this particular case, we have drive lit angle task, which might open the chest like this. And the target angle is defined, bound to a parameter of the whole state tree. There are also other places where you combine the data. So the parameters one, I can highlight here different places where you might find the data. So the first category of the data we can bound to is the context data. And this is basically the data that is always available in the state tree. It means that this state tree was made for an actor component, so we can guarantee that there's going to be a valid actor that you can bind your data to. In this particular case, we can also, if it's for a specific actor class, we can specify that. And in that case, we can poke into the actor's properties to find data. Second thing is state tree parameters. These are basically values you can define. It's almost like the blueprint variables, more or less. And you can set them when you select the state tree asset. So let's say you have a different kind of characters, they might want to have different repetition of something, for example. You could expose that as a parameter. Finally, we have global tasks. I hinted about this earlier. Like they're basically the things that are running all the time, and that the data is always available for all tasks. Also, individual states can be parameterized. They could be useful if you want to use same value multiple times in the tree. And also tasks. So if you remember back that we had active states and active tasks, so you can think active task as like a stack of tasks. And if you have a given task in the stack, it can access the properties of the previous task because we know that those have been already updated. And this can be really powerful for splitting tasks, for finding a point and going to point, that sort of thing. And that's how usually kind of would bind. That's like a really common thing, that you have one task that exposes data or finds data, another task that will basically consume it. And think about inputs and outputs. And go with the previous example. Let's say that we had to go into a point task. It might mark some of these variables be inputs, which means that in that case, we always expect that input to be bound. There's going to be an error that we can't compile the state tree if that's not the case. There's also a way to describe that certain property in your task is an output, which means that it cannot be bound to, and we will not let you set the value because we expect that the code will always update the value, and it has like a specific marker in the UI. And finally, we have context properties, which are almost like inputs with the little difference that they are automatically bound to your context data. And this is useful for reusable tasks like playing an animation. You might play the animation on the current character on the state tree that you build it for, but there might be also another character that you get through, let's say, your target, whatever. A bit funny example given, but basically it can be reusable for any actor, and we don't want to be specific for this particular. So that allows you to, usually when you build a tree, get the really good default value, but when you need to specify and change it, you can do that easily using the property binding. One thing we've been working in 5.5 is binding functions, and these are basically that how to make property binding feel almost like a blueprint. It's a powerful tool, use with care, but this basically can be used for things like you might some float value you want to normalize or to use in some other case, or basically conversion or converting radians to angles or sort of degrees, or combining values. Like in this example, there was a Boolean variable run forever, and we are basically using and binding function to combine two other booleans to basically define when that should be happening. Or you can use one value to get other value. Maybe get component kind of thing would be a thing that you have actor pointer where want to get the component from that. Going a bit deeper, property references. This is for the programmers in the house. There are cases where like property binding works by copying values over, but there are cases where you really would like to write values back where they came from. Or maybe you have really chunky result you want to share, but you don't want to copy like the half a kilobyte of path data, whatnot. And then you can use property references. In the UI, they look almost like the inputs, but in the code, you basically get pointed to the data they're pointing at. And these can be useful for modifying data, like you might have on your state, you might have an int parameter, and you can write a task that will increment that. So if you want to do that sort of thing, that's possible. So you can use the state parameters almost like a blackboard, if that's your thing. Or it can be also used to pass a reference to someone outside the state tree. Like you have a callback and you want to modify properties on your, even maybe on your own or other tasks. That's also a useful thing. Composition. So sooner or later, your state trees get bigger and bigger, or you might have almost the same tree for different characters, and you want to basically reuse that. And this is the composition is all about. There's three types of composition stuff we can do with state trees. One is subtrees, then we have linked assets and parallel state trees. And the point of this is basically just reuse what we built and to be able to work more efficiently. And the idea for the subtrees and linked states, this is like the oldest of all of these things, is that you can create certain states in the state tree which are reusable. These are called subtrees. And then you have linked states where you can basically think that when you link a certain state to a subtree, it's almost as we pasted it in that spot. And that's like easy way for reusing like a specific logic in your tree. I see it in use, for example, if you have attack patterns and you always have certain way for approaching, maybe that's like an easy way for reusing that's part of it. And you use, since they are separate from your current flow on the tree, you can use the state parameters to pass data around. So the linked states parameters are connected to the subtrees parameters. But still, the subtree can use everything that you have globally accessible in the whole tree. The second one is almost like the previous one, but now we are actually able to embed a whole separate asset as like a subtree on our main thing. And here again, we're using the parameters to pass values between the linked asset and the main asset. And this allows things like you can swap a certain part of the tree at runtime, or you can have multiple designers working at the same time on the same state tree. One thing to note about the linked subtrees and linked asset is that in both cases we are sharing the events. So if you send the event on the subtree or part of the main tree, they both get handled. And since they are all kind of forming the same parent chain, as in my previous simpler examples, yeah. So basically, you can think it as like one big tree. And finally, sometimes you need to run two state trees at the same time. And these are usually useful for things that you want to have some kind of secondary behavior which runs on top of the main one. The big difference between parallel trees and the linked trees, even they look a bit the same, is that the linked tree, basically the state selection will traverse into the linked tree during the selection phase, but the parallel tree is run as a task, so it will run after the fact. So basically, once we have done state selection and we have transitioned to a new state, we will start running the parallel tasks. And I've seen them used for things like weapon selection, that you have you're basically paying a basic attack thing, and then you want to run that on top of it. Or some like simple reactions that you can do, kind of overlay on top of your character. And this all is new in 5.5. And here again, yeah, in both cases, the events are shared between the both trees, and the eagle-eyed might notice that there's also a way to define whether the main tree or the sub of the parallel tree gets to handle the events first. And finally, if you want to switch the specific, so you can build your state tree asset with certain, like maybe a default linked assets, but you may want to change them based on the character type at runtime. And this can be done using these linked overrides. And the way it works is that every state can be tagged with the gameplay tag. And then we have a simple lookup table from gameplay tag to a specific asset. And they will be looked at when we start the specific child tree. And one thing to note here is that this works like all the way to the turtles. If you have link tree within link tree within link tree, the same table will be used for overriding everything. So if you have like long nested hierarchies, it will you can override them all. So let's look how state trees are usually put in use. The easiest way to get started with state trees is basically using the actor component, state tree actor component. It works basically on any actor. You can put it on a controller, or you can put it on the actor itself. It's a simple function to start things and stop things. And you can see here like how the state tree reference looks like. I hinted about this earlier. Yeah, and there's one important thing about state trees is the state tree schema. And in this case, if you're creating something for the state tree component, you're going to use the state tree component schema. And the schema basically defines what kind of nodes or what kind of data is available for the state tree. And this is like a really use case specific. We provide in the engine, we have 4 different types. One is the state tree component schema, which only assumes that there's an actor where it's being run on. There's new in 5.4 state tree AI component schema, which extends that you have a reference to an actor as well as the AI controller. There's gameplay interaction schema, which is used for smart objects. And there we basically have a different set of tasks that we can do. There are things, for example, you can set query or set tags on state tree, on smart object slots. There are things that are specific for playing animations on smart objects. And there we have access for the state tree, smart object user, as well as the smart object itself and the slot. And there's a bit more kind of accessible information from get-go. And if you want to extend state tree, the easiest thing is probably creating new task or conditions in blueprints. You can also do that in C++. C++ is more efficient. It will use less data, less memory, and it's packed in memory more efficiently. So it should be more efficient to use that. And if you have your custom use case, you can also create new schemas to basically limit what kind of nodes can be used. And this is like a simple example how it might look like embedding a state tree in a certain use case. There are 3 structs you need to know about. The state tree reference, that's basically how you select the state tree, how you expose your designers, how they kind of they can set the parameters or the overrides. The state tree instance data, and this is the thing that you will basically describes the current situation in the state tree, and this needs to be persistent throughout the frames. And then there's like a temporary object called state tree execution context, which will be used to maybe allocate little runtime, little memory to execute the states and so forth. And that's sort of like a throwaway, like you can see in this example. We're ticking a state tree, and we create the context and resolve some values, and off we go. And state trees do not require an actor or UObject as a parent. So it can be like, for example, we're using it in a mass where individual things are just structs. But we do need an owner, because sometimes we need to create, for example, for the blueprint task, we need to create UObjects. So there needs to be an outer who's going to be the owner of the UObjects. And if you want to look at a fairly simple example, the gameplay interaction context is, if you search that in the code base, that's the one we use for smart objects. I think that's a really good example for running state trees on custom contexts. And then the best kept secret that no one seems to be knowing, but it's been there for a while, is State Tree Debugger. Bunch of people have been asking for it, and they've been surprised that it's there. You can find it in the State Tree asset. There's Windows menu and debugger. You can open it there. It's tracing thing, and it basically gives us an overview and details how the state tree is executing. At top, you can see the active states. They're getting highlighted. At bottom, on the timeline, we can see how the current state is changing. And then on the right-hand side, it shows like what's there, like a really detailed view of that whole thing. You can also set breakpoints on the states. That happens on that on the same panel where you edit the states. So breakpoints on tasks, states, and transitions. You can also enable task and states. When you disable the state, it can't be selected. Or if you disable task, it will not run. And transitions can be also disabled. So it's a really nice tool for pruning down if you want to like execute a really specific case. And finally, there's a way to turn on and off transitions, like enforce all the transitions to be true if you want to make sure that even if you're bug in your own code, you can sort of like still force a transition to run a specific branch if you really want to test it out. So a bit about future. 5.5, one thing showed a bit earlier, we can do a little UI refresh. The data is getting large, trees are getting bigger, so that's something that we're working on. Some hints on that early screenshot, it might look different when it comes out. Utility selectors is ongoing work. I think there's going to be a version of that for 5.5. We're going to still work on more details in the next version. Property binding functions, really useful thing coming up. We're starting to use state trees more for NPC behaviors. So the thing that we noticed there is like how to handle asynchronous things. Like you might have EQS, but you need to wait for it a little bit before it get the results to move to. We try to find better patterns how to handle that. And in general, I think that's going to be coming in further, like next releases. As we build these things up for ourselves, I think there will be more out-of-the-box tools available for building NPCs without having to write your own stuff. One thing that we're seeing with bigger trees is that would be nice to not poll things all the time, but just react to events. So that's like one technical thing that we're looking into how to solve. Small improvements coming to that all the time. And one thing, sort of breaking the patterns on like the common patterns on behaviors like cooldown tickets and counters, like don't do this for that many times, or that's like a really common request. So looking at that one as well. And finally, with the nested trees, the debugger model we have, which is like document-centric, doesn't scale so well anymore because it's really hard to see what happens between nested trees. So we're probably going to take a look at the embedding state tree debugger better with the rewind debugger. So there will be maybe a line showing, a timeline showing what's the current state, and you can kind of then maybe get into specific state tree debugger, which is going to be more actor-centric. So we can show how things kind of progress through the nested trees as well. And yeah, the document-centric was like, that's how BT and BPs are working. So it was like an easy choice early on. If you want something more hands-on, like how to get things done, there's going to be maybe today, tomorrow, very soon, there's going to be your first 60 minutes with state tree in the dev community. It will show how to create wildlife style of AI using state trees. It goes through all the nitty-gritty details how to do that. So that's a good one to look if you haven't used state trees yet. I think that would be really good for getting started guide. There was also at last Unreal Fest, there was a presentation about state trees and smart objects, how they kind of can be combined. So that would be a good thing to look at as well. Thanks.